Welcome to World Decoder. Today we explore the incredible technological revolution driven by the famous Moore Law over 50 remarkable years now. For half a century, computing power has doubled every 2 years, transforming massive mainframes into the sleek smartphones in our pockets. This relentless progress fueled the modern digital age, making artificial intelligence and GDK data networks a reality for everyone on Earth. However, our journey through the Silicon Wonderland is rapidly approaching a terrifying brick wall, known as the ultimate physical size limit. Transistors have become incredibly tiny, reaching microscopic dimensions where they are now measured in mere atoms rather than standard human millimeters. At this incredibly small scale, the fundamental laws of classical physics begin to break down, causing severe instability and extreme heat. Electrons suddenly jump across tiny barriers unpredictably, meaning chips leak massive amounts of power and generate dangerous levels of thermal energy. Manufacturing these fragile, microscopic structures has become harder than ever, pushing traditional fabrication plants to the absolute brink of their capabilities. Without a massive structural breakthrough, the phenomenal growth of artificial intelligence and cloud computing will soon hit an insurmountable performance ceiling. Our beloved smartphones would stop getting faster, and data centers would consume unsustainable amounts of electricity just to maintain basic operations. Fortunately, deep inside a highly secretive research laboratory located in Belgium, brilliant scientists are actively working to save the tech industry. This legendary facility is known as IMECA, Neutral Innovation Hub, where fierce rivals collaborate to solve the hardest engineering problems. Tech giants like Apple, Nvidia, and Intel all rely completely on IMEC to chart the future roadmap of advanced semiconductor manufacturing. Inside these pristine clean rooms, researchers wear protective white suits to prevent even a single speck of dust from ruining complex experiments. They have recently developed a revolutionary new transistor architecture called CFET, designed specifically to overcome the dangerous limitations of older designs. For many years, the industry relied entirely on FinFET technology, which featured tiny silicon fins sticking up from the flat surface. These vertical fins allowed engineers to pack more processing power into smaller spaces, keeping the Moore Law alive for another entire decade. But as we pushed the boundaries further, those delicate silicon fins became incredibly thin, fragile, and prone to breaking during production. Shrinking the flat surface area was no longer a viable option, forcing scientists to rethink the entire geometry of modern microchips. Instead of spreading components out horizontally, the brilliant minds at IMEC proposed a bold idea to stack transistors vertically upon themselves. This vertical stacking approach is exactly like building massive skyscrapers in a crowded modern city, where available land has completely vanished. By building upwards, engineers can effectively double the transistor density without needing to shrink the fragile horizontal footprint any further. Today, the CFET architecture elegantly stacks two different types of transistors directly on top of each other, creating a highly efficient tower. This brilliant vertical tower design drastically reduces the distance electrical signals must travel, boosting overall processing speed while saving battery life. To achieve this incredible manufacturing feat, engineers must operate at a microscopic scale, where normal visible light simply cannot penetrate anymore. Researchers utilize powerful transmission electron microscopes capable of magnifying these tiny structures 50 million times to observe their exact atomic composition. Through these advanced lenses, we can clearly see conductive channels that are incredibly thin, measuring just about 30 atoms across today. We are literally touching the absolute boundaries of our physical reality, manipulating matter at the most fundamental level of its existence. In this extremely delicate environment, even the smallest microscopic particle of dust could instantly destroy a priceless million-dollar scientific experiment. The challenge extends far beyond architectural design. It requires completely new industrial equipment to manufacture these complex vertical towers in bulk. To physically print these tiny CFET structures, the semiconductor industry desperately needs next-generation lithography machines utilizing extreme ultraviolet light technology. These massive engineering marvels, known as high-NA EUV systems, are incredibly complex and cost an astonishing $200 million. They use incredibly precise mirrors to focus invisible light beams, carving microscopic patterns onto silicon wafers, with absolutely flawless atomic precision. Transporting just one of these gigantic machines requires multiple cargo planes and dozens of specialized shipping containers to ensure safe delivery. Once installed inside the fabrication plant, these machines must operate in a perfect vacuum to prevent air molecules from absorbing light. The successful integration of CFET architecture and advanced EUV lithography promises to keep the semiconductor industry thriving until 2030. This powerful combination will enable the creation of smarter artificial intelligence systems, more powerful smartphones, and incredibly efficient global data centers. However, looking beyond that upcoming decade, the ultimate roadmap for silicon technology remains shrouded in deep mystery and complex scientific uncertainty. Even with vertical stacking, there is a fundamental limit to how many transistors we can safely pack into a single microchip. Heat dissipation becomes an insurmountable nightmare when billions of microscopic components operate simultaneously within a space smaller than a human fingernail. To solve this looming thermal crisis, researchers at IMEC are actively exploring alternative pathways that completely abandon traditional electronic circuit designs. One of the most promising new frontiers is silicon photonics, a revolutionary concept that uses pure light instead of electrical currents. By transmitting data through microscopic optical fibers built directly into the chip, we can drastically reduce energy consumption and boost speeds. Light travels much faster than electrons and generates practically zero heat, making it the perfect medium for future high-performance computing. Imagine a future where computer processors communicate with each other using tiny lasers, creating a dazzling microscopic light show of information. However, integrating fragile optical components with standard silicon manufacturing processes presents a monumental engineering challenge that requires years of dedicated research. IMEC is also testing exotic new materials that could eventually replace silicon entirely as the foundational building block of modern electronics. One fascinating candidate is graphene, a single layer of carbon atoms arranged in a beautiful hexagonal lattice that conducts electricity perfectly. Carbon nanotubes offer another exciting possibility, forming microscopic conductive wires that are significantly stronger than steel and highly efficient at cooling. These advanced nanomaterials could allow us to build processors that are incredibly fast, remarkably durable, and completely immune to decay throttling. Transitioning away from silicon would require rebuilding the entire global supply chain from scratch, an endeavor costing trillions of modern dollars. This is exactly why the collaborative model at IMEC is so crucial for the continued survival of the global technology ecosystem. By pooling their immense financial resources and sharing early research data, competing companies can collectively afford these astronomically expensive scientific experiments. Operating as a neutral nonprofit organization, IMEC truly acts as the master chef for the most complex chip recipes worldwide. They carefully test thousands of different chemical combinations and structural designs before finalizing a reliable manufacturing process for the entire industry. Once a specific manufacturing recipe is perfected inside their Belgian laboratories, it is securely shared with mega factories located across Asia. Companies like TSMC and Samsung then take these proven formulas and scale them up to produce billions of chips every year. This incredible global partnership ensures that the bright flame of technological innovation will never be extinguished by daunting fundamental physical barriers. Every time you smoothly swipe your modern smartphone screen, you're directly interacting with decades of collaborative genius and relentless perseverance. The journey from bulky vacuum tubes to atomic-level transistors represents the most impressive and sustained human engineering achievement in recorded history. As we stand on the thrilling precipice of the quantum computing era, the foundational lessons learned here will guide future generations. The relentless pursuit of smaller, faster, and more efficient processors is no longer just about making better consumer electronics for entertainment. It is now fundamentally about solving massive global challenges like climate change, advanced medical research, and complex space exploration missions tomorrow. Supercomputers powered by these next-generation chips will simulate complex weather patterns with unprecedented accuracy, helping us prepare for natural disasters. Medical researchers will utilize immense processing power to discover life-saving drugs and personalized treatments based on individual human genetic profiles. Artificial intelligence models will become exponentially smarter, seamlessly translating languages in real time, and driving autonomous vehicles safely through chaotic streets. None of this bright future is possible without the silent, unseen revolution happening continuously at the microscopic atomic level right now. The engineers at IMEC are the unsung heroes of our modern era, quietly pushing the boundaries of human knowledge and capability. They do not seek public fame or massive individual wealth, but rather the profound satisfaction of solving the hardest puzzles on Earth. When we look closely at a modern silicon wafer, we are actually seeing a beautiful mirror reflecting our collective human ingenuity. It is a profound testament to what we can achieve when we stop competing destructively and start collaborating towards shared goals. The story of the famous Moore's Law is far from over. It is merely transitioning into a thrilling new chapter of expansion. From flat plains of silicon to towering microscopic skyscrapers, our digital infrastructure is evolving exactly like a sprawling futuristic metropolitan city. We must continue investing heavily in fundamental science and education to ensure the next generation of brilliant engineers is always ready. The challenges ahead, from mastering silicon photonics to synthesizing stable graphene structures, will require unprecedented levels of international cooperation and funding. But if the past 50 years have taught us anything, it is that human creativity knows absolutely no bounds or limits. We have consistently transformed seemingly impossible science fiction concepts into everyday reality, reshaping the entire world in the process time again. The microchip revolution stands as a shining beacon of hope, proving that dedicated scientific inquiry can elevate humanity to unimaginable heights. As we forge ahead into this exciting, unknown territory, we will continue to decode the fascinating mysteries of our digital universe. Thank you for joining us on this incredible deep dive into the microscopic world that secretly powers our entire modern civilization. We hope you gained a profound new appreciation for the staggering complexity hidden inside the everyday devices you use so frequently. Stay curious, keep exploring the wonders of technology, and we will see you next time, right here on the World Decoder.